Okay, so today's Monday, March 29th. Homework 9 was due today. Homework 10 is due on Wednesday. Homework 11 is due on Monday. That will be an exam 2 review. We put off some of the homework just because so I could catch up. You have all the material you need for homework 10 already, all the class material. Homework 11, we're going to start covering today and we'll finish it on Wednesday. Exam 2 is Wednesday, April 7th in Frankie 436. Want to take it online, send me an email and we will schedule a time. One more lab and one more homework after that. We start lab 6. It's a 2-week lab. It is on inverters, different ways you can build an inverter. And then we will have the final exam. Oh, yay. Last semester, it was, I hate to tell you this, it was on a Friday at 5:30 or Saturday at 5:30. It was something awful like that. Let's see if it came in. Zach Price, I got you. Jordy is another person I'm looking for. Lauren, Jordan Ramirez, and Ibrahim. Okay. So, yeah, alert chat. Anything in the chat? Nope. Okay. So this is the MOSFET as is shown in the Cedra Smith book. It is last decade's technology, but it lasted about 30, 40 years. In the planar form, we just build it a little bit differently. There's still MOSFETs around. And we've talked about this slide a lot, and this is the picture of what it looks like. I have a gate up here. The gate is a capacitor. It's a big piece of metal with a very thin oxide and 2 parallel plates. The other plate is the actual substrate of the transistor. It's called a MOS capacitor. I have source and drain diffusions at either end for an N-channel NMOS device. NMOS stands for N-channel metal oxide semiconductor. I'm answering some of your questions from the quiz as I go along. These are the primary device that is used in most electronic circuits. If you're thinking about a processor or you're thinking about any kind of logic circuit, any kind of digital circuit, it's going to be built primarily out of MOSFETs with a few BJTs around there. So most electronics is all MOSFETs now. And that's why we've been shrinking the size down as time goes on. Now to get them down to about, this took place around 10 nanometers, they found they had to take this planar structure. Here we've got the source and drain, it's buried. The channel is actually buried in the substrate. This is where the line I drew is where current flows. What we're going to do here is we're going to have current flowing above the substrate and wrap the gator all around it. And you got so much better control, and it was such a better MOSFET that most people are doing this now. To get that worked from about 10 nanometers down to about 5 nanometers, now Samsung's in early production on 3 nanometer devices, which look kind of like this, except for the gate is wider because the wires didn't work. They needed what they call sheets, which is just a little bit wider area. They had to make this dimension bigger. Okay, and you'll learn all about that in 380 or when Dr. Campbell comes. And we'll learn all about it in device physics, and you'll learn about it in semiconductor memories and all the other good classes we have. A lot of microelectronics in Arizona. If you want a job as an electrical engineer in Arizona, microelectronics is a very safe bet. So we're going to start out with MOS analog. Now, analog is different from digital in that we care about discrete values. A difference between 1.1 volts and 1.2 volts really matters in an analog design. And we're going to start looking at the most basic function of MOSFETs and that, or analog circuitry, and that is amplifiers. And amplifiers and amplification and what we mean by that. You've already encountered amplifiers in EE188 with op amps. Op amps are great. They are the building block of a lot of discrete analog circuitry, and they're the building block of a lot of analog stages inside an integrated circuit too. Now, this is what we mean by an amplifier. It's got some input and it's got some output. The input could be coming from something like an antenna. And with an antenna, you're going to have very small power levels coming in. So the first thing you want to do before you have to actually drive anything with it is amplify that signal and make the voltages and currents larger. So I have an input that is some small signal. It could be a sinusoid. It could be a triangle wave. It probably looks more like a voice signal where it's more random, or a data signal, which is more random. But this is a good place to start. So I have a small input, and I want to turn it into a larger value of voltage or current or power at the output. Now, there's more than two kinds. There's three kinds on this slide. There's two basic ways I can put the input in. The first, the input could be the difference between of a signal. I hook this up to an antenna. What does an antenna look like? Like this. I hook this up to an antenna, and I'm referencing this to the antenna's ground, not to my system ground. This is called a differential input. It's amplifying the difference between two signals. And I could have an amplifier with a differential input and a differential output. The output isn't referenced to system ground, it's referenced to itself. So it's a difference between those two voltages. I could have a single-ended amplifier. Now here, the input is referenced to my system ground, and my output is referenced to my system ground. So this is single-ended, and what we'll be doing in here mostly is single-ended. This is differential. Now, if you think about the op amp that you have experience with from 188, it looks like this in its most basic form, plus, minus, out. This is a differential input because what this amplifier actually, what the amplifier actually has gained, I realize you don't know all this terminology yet. What the amplifier actually amplifies is the difference between these two signals. This is called VN differential. And so this has both a differential end and a single end on it. The output's referenced to system ground, and it gets information about system ground by, it's got power supplies, V minus, and several of them, if they're precision op amps, will have also a pen that you have to drive to ground, so it knows, the device knows where your ground is. Now that's the model you looked at, and we looked at a really ideal model of an op amp in EE188. In reality, when you're dealing with these, you've got to think about a lot of things. They have input resistance. They have output resistance. The output resistance limits the amount of current you can drive from them and how small of a load resistor you can put here. Your load resistance has to be bigger than Z out. So it's good to know what Z out is, or R out. And this resistance right here leads to a non-ideal voltage across these two terminals. A really precision op amp, that difference between the input and the output terminals is not zero, but it may be 25 microvolts. It's really small. Whereas you use the 741 like you did in the 188 lab, it probably has a differential voltage around 50 or 100 millivolts. So significant difference in the specifications. There are literally thousands of op amps on the market. Everyone is designed to suit a specific set of needs. And sometimes it takes me a week to pick out an op amp just because I'm looking for something that's just right. Those details we won't get into in this class. That's like $490 in the fall. Okay, so what do we mean by gain? We're going to again, this is an example of linearizing a very nonlinear circuit. And by linear, not all lines are linear according to the engineering definition. They also have to be lines that pass through the point 0, 0. They have to pass through the origin in order to meet that linearity specification to qualify as a linear circuit. So if I think about this, I've got a circuit, I've got Vn, and it can be a function of time. And out of this, I'm going to get some V out, which is also a function of time. And if I look at my circuit here, depending upon what Vn and V out is, I get something that hopefully looks like a straight line in the region I'm talking about, and it has a slope of AV. That's just basically the slope of that line. The voltage gain, it's the slope of that line. So that is, you know from calculus, that is the derivative of V out with respect to Vn. Delta V out over delta Vn if you're being a little bit sloppier. If you're being a really sloppy engineer and you say, well, I'm operating around this operating point right here, and it's fairly linear in the region that I'm going to be using it, I can just calculate the V out over Vn, because again, it has to pass through the origin. So this is the definition of voltage gain. Yes, the 380 students just had their exam where every question calculate Rn, R out, and the voltage gain. This is when I want my voltage signal levels to get higher. This is usually what we call an amplifier. If I want my current to get bigger, this is usually what we call a buffer, because it's not amplifying voltage, it's amplifying current. So I usually put this in places where I have a tiny little transducer, like a little piezoelectric microphone that's picking up some really small signal, and it's incapable of driving any kind of current load. So I put a current gain in the system to fix that. So AV for voltage gain, AI for current gain, and sometimes you want to amplify both current and voltage, so we talk about power gain, AP. And AP is just basically defined as the load power out, the power out over the power in, which also should equal the current gain times the voltage gain. Right. Okay, so we want to calculate some gains. Yeah, I usually put this like, it usually ends up on an exam somewhere. AV is going to be V out over Vn. We've got 10 over 0.1, should be around 100. And if we want to calculate that in dB, the voltage gain in dB is going to be 20 times the log of 100. In that case, that should be 40 dB. Now, if I want to calculate the current gain, my AI is going to be I out over IN, assuming it's linear. And I out is 2 milliamps. IN is 100 microamps. Did I calculate that? No, of course not. I skipped that step. And there's a reason why I have my calculator out. E minus 3 divided by 100, E minus 6 gives me 20. And if I want to find the current gain in dB, it's going to be 20 log of 20, which is going to be 26 dB. Now, if I want to calculate the power gain, it's going to be V out, I out is the output power. The input power is Vn, In. And so we have 10 over 0.1 times 20. Yeah, I just don't get to add those together. Otherwise, I would just do that. Over 2 milli over 100 micro. And that comes out to be, sorry, there's a phase, 10 times 2e minus 3 divided by 0.1 times 100. E minus 6. You think I could do this in my head? This is 2,000. The reason why I can't is because I'm going to screw it up because this changes here. AP in dB, the formula is different. It's actually 10 log of the gain, and this comes out to be 33 dB, which is exactly half of what you get if you added the current and the voltage gain together. Something else important I wanted to say here. Oh yeah, AV, it's dimensionless because I'm taking volts and dividing it by volts, but a lot of times engineers stick in the units volts per volt just to remind people that it's a voltage gain I'm talking about, and AI, amps per amp, and AP is watts per watt. So that's usually the way we differentiate those. A lot of engineers out working in the analog world, they talk in dB. They don't talk in voltage ratios. So it's a good skill to have. It allows you to talk about things that are changing by large orders of magnitude, like they're linear. Now this is a symbol convention. This is what Cedra Smith uses, and this is what a lot of the textbooks use. We have two different types of signal that we're going to be dealing with here. There's a DC part of the signal and there's an AC part of the signal. So on one side of the equation, I have a quantity that looks like AC plus DC, and it's just written as one term. And on the other side, I have the AC component of that plus the DC component of that. So DC is usually written as capital I, capital C. And I'm going to put an underline under that because I can't tell the difference between a small c and a big C. The AC part of this is written as little I, little c. And the total signal, the AC plus the DC, is written as little I, big C. And if you read the Cedra Smith book, it makes a whole heck of a lot more sense if you know this convention, because all of a sudden the I's just change case and it's a completely different thing. So it's important to kind of know that convention. And if I look at this diagram, the DC part of the signal is big I, big C. So that's my DC part of the current right there, part B. That's just the average value of the current is my DC component. The total, let's do something that makes more sense. The instantaneous signal current, so that's the amount of current that I have in the AC portion. This is usually written as AC, IC as a function, IC as a function of time, is little I, little c. So that's part C right there. The peak amplitude is the fourth way I can write this. This is big I, little c. And the peak amplitude of the AC is just the difference between the average value and the peak value. How much of that signal is actual AC? And the total instantaneous current at any given piece of time is little I, little c. This is the AC plus the DC part of this, and that is right up here. So that's the total current at this particular point in time. Little I, little c. This is what I call DC, and this is what I call AC. Or wait, no, AC, no, wait, total instantaneous current. And then this is the AC part, the peak amplitude. Okay, and that can be a function of time too. So that will help you in your reading of the Cedra Smith book. You think you have to read a lot for this class. When we get to 380, it's a lot more reading because there's just not enough time, class time, to actually go through and do every possible example in the book. So you have to dig through the book and read. You have to find equations in the book for the pre-labs and things like that. All on your own, and we may not talk about those necessarily in class. Okay, so here's the big picture. I've got, remember the voltage transfer curve? We talked about this. This is when the transistor's off, if it's a single NMOS transistor. This is when it's in triode. I think I just skipped ahead of myself. And the region between A and B is saturation. And this is what we use the saturation region for. Yet another one of the questions that came off of the pre-lecture quiz. What I want here for an amplifier is I'm going to put a very small signal on VGS. So I've got some DC value of VGS right here that's greater than V threshold. And I add some small signal to this. And as little v, little g, little s reaches its minimum value, I'm at this operating point right here on the VDS axis, which means my output voltage, my VDS, should be about right there. And when I hit the positive peak on my little v, little g, little s, I'm going to move the operating point down here, and my output voltage, little v, little d, little s, is going to be about right there. So my output voltage is going to have a much larger swing than my input voltage, and I can achieve this idea of having voltage gain. So two different parts of the signal, and we'll be doing a lot of divide and conquer, kind of like superposition. I have a DC value of VDS. I have a DC value of VGS, and my signal is going to swing around that value. So my signal the total signal is the two of them combined together. Okay. And your subliminal message of the day, motivations, what feeds success. These transistors, I have been, when I got to this in college, I was like, I didn't feel like I understood them. And even today, I feel like I understand them much better, but there's still things I'm learning, especially when with the change to FENFETs, the physics changes, and that just is what makes it all interesting. And whatever motivation you have, whatever you feel motivated to do, that is what you'll be successful at, not what someone else thinks you should be doing. A lot of people slog through college to get the job as an engineer so they can do what they really want to do, play music, do art, and have enough money to do that on the side. Or what Keith Caldwell is doing now is building hopped up cars. So what we have here, 3 different regions of operation. If VGS is less than VT, then we're in cutoff. And we can see here, this is our VGS axis. If it's less than VT, we're in cutoff. So this is my cutoff region. If VDS, so I need VDS big, VDS is greater than VGS minus VT. So I need VD big. I want VDS kind of up in this region. And I want VGS small. So this is the VGS axis. I want it down here. This must be that I'm in saturation. So this must be the saturation region. And if that's not true, if VDS gets really small, this is the VDS axis, so this is my small VDS. If it's small, then I'm going to be in triode. Okay. And so what I want to do here is I put a DC signal on the gate that puts me at this Q point. So this is my big V, big G, big S right here. I put an 8 AC signal in series with it. So they're going to add. And I put those both on the gate. There's my AC signal, my little v, little g, little s. I put that in on the gate, and my output I want to take off the drain. So this is V in, this is V out. I'm going to take my output right off of there, and we can see at that point VDS will have both its DC component from its operating point, and that's the DC component right there, DC, plus the swing of the AC. We use saturation because it's the only place I have the slope that gets me the gain. Good. I think I covered that. I got a bunch of questions on that in my pre-lecture. So this is called a common source amplifier, and it's the best single transistor amplifier if you want voltage gain. The others have other processes. This is the only one we're going to look at in this class. We'll look at the others in 380. So the first thing I do when I'm designing this, I pick a DC bias point. And I want to pick, for best linearity, oh no, I shouldn't start this. I'm going to just pick the operating point in the middle of the saturation region so I can get the maximum signal swing out of that. There's a few other places you might want to pick that. But we're going to pick a DC bias point Q, and for right now, we'll call it just right in the middle of the saturation region. And from that, we can determine what DC values we need to get it at that bias point. And this is called the Q point. The Q point is just the DC operating point. And if I want to figure out, if I ask you, and I had a whole senior class on op-amp design, and every single question on the exam was had started out with what's the Q point, and I had no idea what Q point was. It's just this. And so I said, I have no idea. I'm just going to calculate ID, VGS, and VDS, which was exactly what he wanted. Okay. So the Q point is the DC operating point, and the three that really matter are those three right there. We can use the DC values of ID, VGS, and VDS to calculate some small signal parameters. And this is little gm and little RO. And these are what are going to determine the gain of the transistor. So once we get gm and RO, we can look at the small signal model of the transistor and calculate the gain. This is an example that we're doing here for the common source amplifier that looks exactly like this. It is not a general method, but we will look at the general methods in EE280. In fact, they just had the exam on that. So if I start yelling, it's because it's hard learning some of this stuff online. I ended up having to give them 10 points on the exam just to get the average up to like a 70 or something like that. It was really bad. There's like one person who made a 98, of course. Now they have 108. So this is called the common source amplifier, and I'll explain why it has that name. First off, I'm putting, this is little v, big G, little v, big G, big S. So it's both AC and DC in a single source. And so my signal is coming in here, and this is what I call the signal path. And the signal is moving from the input is on the gate, the output is on the drain. So I call this a common source because the source is an AC common and AC ground. And that's where the naming convention came from. And we want to figure out what's going on here. First thing is, what operating region is it in? We're checking to make sure we did this right. So we have, is VGS greater, I wrote it the other way, less than VT? Well, our VGS is 0.55. Our VT is 0.4. No, it's not in cutoff. And the next thing we want to figure out, I'm just using this set of rules over here. I actually have these memorized. If VDS is greater than VGS minus VT, then we're in saturation. My VDS is 1.0 volt. 1 volt. Is that greater than 0.55 minus 0.4? And that is not true. So wait, it is true. Never mind, it's in saturation. So we know this amplifier's in the right region. When I was teaching at a tech school and we built these amplifiers, generally one of the first things, and it wasn't working, one of the first things I would check was what's VDS and what's VGS, and see if the amplifier was actually in saturation. And that was usually what was going on and why it wasn't working. So we'd have to fix that. Now, if VGS goes up, this is the equation for current in the saturation region right there. So if my VGS goes up, my ID also goes up because will go up like VGS squared. ID will also increase. Now, if ID is increasing on this diagram, my V out is VDD minus the voltage drop across that resistor, IDRD. So if the current goes up, this voltage is going to go down. Doesn't look like it'll make an amplifier, but from the diagram we've already seen, when little VGS is at a minimum, this is at the output, VDS is at a max. When this is at a max, the output's at a minimum. So it is an inverting amplifier. It has a negative gain, is the reason why this works as an amplifier. VGS goes up, V out goes down. But it goes down by a larger amount than VGS goes up. Okay, so these are typical signals, and you get to plot these in 380. I have little v, big G, big S. It equals a DC, which is a time varying signal. It equals a DC value, not a function of time, big V, big G, big S, plus little v, little g, little s. And if we plot that, we get the DC value is the average value that you would see on your oscilloscope, whereas the signal is kind of small right there. And same thing for VDS, there's a DC level and there is a larger AC component. And if you actually plot these on an oscilloscope next to each other, what you see is the peaks on the input correspond to the minimums on the output. And this is what, it's a gain of -1, which can, or a negative gain, which is also the same thing as a 180-degree phase shift. So we know this is shifted in phase by 180 degrees. Usually people just write it as a negative sign. Controls engineers love the phase shift thing. It leads into one of their big stability criteria. Okay, 18. Now, if the transistor's in saturation, we know the transistor current is going to look something like this. ID equals Kn prime over 2. I agree. W over L VGS minus VT squared. So that's the equation for the transistor current. The equation for the resistor current equals IR. I is going to equal the voltage drop across the resistor, which is VDD. It's always a V is always a voltage difference, minus VDS or V out over RD. Remember, voltage is always a difference, and I'm going to whack my 380 kids on the head for that. A lot of them missed a lot of points because of that. VDD minus VDS. So these two are in series. The current through the resistor is exactly going to equal the current through the transistor. So we know that these two currents have to equal each other. I'm not going to try to rewrite that because it's on the next slide. This is the current through the resistor is right here, VDD minus VDS over RD. The current through the transistor is right there. They're in series, so they have to equal each other. Now we could rearrange that, and this is just another form of Ohm's law right here. Remember, it's VDD minus VDS equals IDRD. If I rearrange it a little bit and solve for VDS, I get VDD minus IDRD. So that's another way of doing it. Or I could just plot and do algebra on this equation. I get VDS is going to be VDD minus that saturation current equation, Kn over 2, almost RD times VGS minus VT. Now, my output curve, this is in the saturation region. It's in this region right here. It looks like a straight line, but it really depends quadratically on VGS. So that's really a parabola. It's some kind of parabolic curve. It's a piece of a parabola. So it's not as linear as we think. We want it to be a straight line, but it's not going to be exactly there. Going from cutoff to saturation, what's going to happen is VGS will be less than VT. So this point right here is going to be, the x coordinate's going to be at VT, and the y coordinate, if I'm in cutoff, I have 0 current, and if I have 0 current going through here, my V out, my VDS would be VDD. So we've got this point right here is at VDD, VT. Coordinates of B, it's messy, and we'll look at it on the next slide, but I really don't like talking about it very much because it's kind of useless. People who are trying to design their amplifiers to have the best signal swing, put their Q point here. Q, best linearity, and max signal swing, let's call it that. People who are trying to design an amplifier that works but uses minimum current move their operating point this way. So this is the minimum current point. People who operate their transistors down here are crazy. There's no advantage to this whatsoever. You both have bad linearity, small signal swing, and you have high current. So it's like the worst of all possible worlds. So this is the region that we care about the most, putting our cue point somewhere between the middle and the minimum in order to get the linearity ID trade-off. But if you did want to find the coordinates of B, they are on the next.
Sorry, can I ask you a quick question?
Yes, go ahead.
On that last slide, would you say at point A is the minimum?
Point A is the minimum current, right?
Okay, all right, thanks.
Yeah. And you see, there's all kinds of tricks people use to get the current to a minimum. One of the things they use is something called pulse width modulation that you'll see a lot. The Arduinos use it for their analog output, but it's used a lot in power circuits to minimize the amount of power you're losing, which is a big deal for power people. If you're trying to build the perfect audio amplifier with the best speakers, you put the cue point in the middle. If you're trying to build an amplifier that works for your cell phone but doesn't drain your battery, you start moving the operating point up this way. If you move it down towards B, it's a mistake. It just doesn't work. Okay. So let's not talk about that. Let's talk about the load line a little bit. We won't see this on the homework or anything, thank goodness. This always confused me, but it's fairly simple here. Now I have I say that. This is the this is kind of like this is ID here. So this is an AC current plus a DC current. Now I can set this thing for ID, but if I have AC signal coming through here that varies through time, I could end up at some point in my signal instantaneously where the AC equals the negative of the DC. And when that's true, I have zero current. So that's the minimum current I can get out of here. And if I'm at that point and I have zero current, my V out, because it's just going to be determined by the voltage drop across the resistor, is going to be 1.8 volts. So I found 1 volts. I found 1 point of my line at I equals 0, which is, this is the I axis, so that would be this point right here. My V equals 1.8 volts. So there's 1 point on the line. Now the next thing I could be doing, let's say AC is a large positive value. I could get to the point where I have the maximum amount of current here is going to be, the maximum amount of current I can get out of the circuit is when this voltage is 0. And to get 0 volts, my current would be I equals the voltage difference, 1.8 minus 0 over 10K, and that's 1.8 over 10K, should be 180 microamps. So that would be this point right about there. So if V is 0, my current is 180 microamps. Now, as long as that resistor is acting like a resistor, it's going to behave, it's going to follow Ohm's law. And the only possible currents that I can get through this are going to be on a line between these 2 points. That's a straight line with an even slope everywhere. So my operating point, because of the resistor, has got to fall somewhere along that line. Now, remember, if the transistor is behaving like a transistor, it's going to be operating along one of these curves. There's a halfway curve, like at 1.7 volts in between here. And we can look at this, put the load line on across the transistor curves, and pretty quickly determine what is the minimum voltage to keep it in. We want to keep it in saturation. So this is a nice parabolic curve. It's going to be somewhere right about here at about 1.2 volts of VGS. These are VGS. Then I'm going to get the transistor into saturation, just at the edge of saturation. If I want to get it more in the linear range, I may have to operate it more out here at a lower value of VGS. Okay, that's all I want to say about the load line. I should just, yeah. Okay. And I'm not going to talk about old engineers. The people who were old engineers when I first started working were really good with these load lines. A lot of people now are more dependent upon computer analysis. Even I was more dependent upon computer analysis than that. But some of these guys can take out a napkin and figure out instantly what voltage you want to operate at. And I had to think. Okay. So the voltage gain, we said, is the slope of the line at this point and the slope of that line is going to be the derivative of VDS with respect to VGS. And our V out is VDS for this amplifier, and our VN is VGS. So we've already developed an equation for VDS in terms of VGS. So taking the partial derivative, I just put things like ID and BDD and RD and K and everything else in that equation gets treated like it's a constant. And I take the derivative of this equation. What I get is minus KN RD VGS minus VT. That is the gain of a common source amplifier as it was as the circuit was drawn in this earlier in the slides. It's not the gain of every common source amplifier. Some of them don't have RD in there. Yeah. Some of them have more resistors in there, which makes it more complicated. But for the circuit we've done, we've derived the gain that works for that circuit. It's a fairly common topology, but not used everywhere. Okay. So we get three equations for gain. Basically, I've got a bunch of equations here, and I can algebraically manipulate them. There's the first one, the one we've already looked at. Remember, VGS minus VT is also called V over voltage. So this is a really common form of this because this VGS minus VT shows up a lot in the equations. We gave it a special name. We can also manipulate some of these, some more of these equations right here and get negative IDRD over VOV divided by 2. Now, the thing we can get out of these gain equations is, as a designer, what do I do if I want to increase the gain? There's only a couple of things you can do here. I could make KN bigger. That would mean I would have to buy a better transistor. Or if I was an IC designer, I could make my transistor bigger. I need to make VTN smaller. So these all fall under the category, those two fall in the category of getting a better transistor. Not always an option. Sometimes it is. The other thing I can do right off the top of the bat is I could make RD bigger. And making RD bigger is just going to the parts cabinet and picking a different resistor. That's fairly easy to do. The other thing I can do is I can make VGS bigger. But if I make VGS bigger, I'm also making the current bigger. But any one of those things should increase the gain. And the limits are pretty much, if we go back to that circuit, VN V out. We cannot have V out greater than whatever VDD is. I can't get more voltage out of here than I put into the circuit. So we can't increase the gain until I get to the point V out cannot be greater than VDD. And also V out can't be less than ground. Cannot be less than ground. So either one of those two conditions, I'm limited by the power supply voltages. Unfortunately. And the other thing is I have to keep the transistor in saturation. So I've got a few more constraints in there. And we'll talk about those much more in 380. The sad part is when the transistor goes out of saturation, it stops amplifying. When you know what engineers call that, when you hit the rails because you're no longer in saturation, your circuit stops working. Unfortunately, we call it saturation. Okay. Just, yeah. It's something you've probably seen in the 188 lab. You put an AC signal into an op amp and you're expecting an AC signal out, and what you get is something that looks more like this with these flat tops in it. That is your amplifier going into saturation. It's hit the maximum value, DC value that it can put out, which is caused by your amplifier going out of saturation. I just have to say that. So we're going to match the variables to the waveforms. I've got an input here, two pieces of it. There's a signal voltage, and my signal voltage on the input is little v, little g, little s, and we're expecting that to be small and have no DC component. So this is, one is little v, little g, little s. My DC value at the gate, remember we need VDS to be greater than VGS minus VT to keep it in saturation. So I'm expecting my DC value at the gate to be smaller than my DC value at the output. So I'm going to look for the smaller version of this voltage. So this is probably my gate to source voltage because it's smaller than the other DC one right here. So this one right here is big V, big G, big S, little v, little g, little s. And the other one at the gate would be the total signal. If I add those two together, if I add 1 and 2 together, I get 4. I get the DC value plus the AC value. This is little v, big G, big S. For the one that looks like this. And we can do the same thing for the drain to source. There's a DC component right here. This is big V, big D, big S. That's 5. No, wait, what am I doing? Do you guys let me get away with that? I'm just saying things at random. The DC component right here is big V, big D, big S is actually number 6. The AC only component is number 5, little v, big D, big S. And the sum of them two was the sum of the two. No, I'm doing it again. I'm getting tired. Let's just do this over again. The DC is big V, big D, big S. Yes, I agree with that. The AC only is little v, little d, little s, 5. And the AC plus DC is little v, big D, big S. Yeah. You'll get to plot these when we get to 380. They just had that exam. Okay. So I've got this amplifier, And I'm given a lot of things about it. I know what transistor it is, so I can look up VT on the data sheet. I can look up KN prime on the data sheet. Well, I can probably look up KN on the data sheet. My lambda 0, that just doesn't matter for this one. VDD is 1.8, so I'm going to write that on the schematic. My RD is 17.5K. And my VGS is given, the DC part of VGS is 0.6 volts. We're going to do a DC analysis here. And my AC part of the signal is 10 millivolt sine wave at 100 kilohertz. So it's a magnitude times the sine of omega t. Because this is omega, which is in radians per second, we have to multiply the frequency in hertz by 2 pi. So the first thing we want to find is V over voltage.
Hello. Also, Josie told me she put you as a Herland plot. Like if you call them, you can tell them also on Herland Lord and her.
I don't think that has anything to do with class. Okay.
Okay.
And that was not who was talking. Okay. So V over voltage is going to be the DC part of VGS.
Yes.
VT.
You already talked to them? Yes. What did they say? They ask like we smoke, we stink.
Okay.
Yo, bro, chill.
Okay. If you have a real question, say it. You can say it out loud, or you can do it in chat. Okay. So the VOV is we're doing the DC operating point here. I'm not thinking about what's going on with the AC. So I just use the DC value of VGS. It's 0.6 minus 0.4. So my VOV is 0.2 volts. That's pretty straightforward. That's as straightforward as it gets. Now I want to find ID. And to find ID, I assume saturation. So ID is going to equal Kn prime over 2 W over L VOV squared. So my Kn prime is 400 micro divided by 2. My W over L is 10 and my VOV is 0.2. And that comes out to be number 11. That comes out to be 80 microamps. Pretty typical value. You're going to get microamps and milliamps and things like that. Okay, so we got that. I'm going to write that on the schematic because the next part is I want to figure out what VDS is. Well, I know I've got a resistor. I know the voltage on one side, the current and the resistance. I can use Ohm's law to find VDS. So my VDD minus VDS is going to equal IR. That's just Ohm's law. And if I saw that for VDS, I get VDS equals VDD minus IDRD. I can actually say that really fast because I've done that a lot. But it's 1.8 minus 80 micro times 17.5K. The way I know I made a mistake here, I made a really bad mistake, is if that number comes out to be negative, then I go through and check everything. VDS is going to come out to be positive. So we got our VDS, we got our ID, we got our V over voltage. We can use that formula to calculate the gain. The gain is KNRD VGS minus VT. This is also, remember, KN is just KN prime W over L. And VGS minus VT is VOV. So we can get the voltage gain I'm just gonna do it up here. AB, there's a negative sign in there. 400 micro times 10 times what the heck was our RD? RD is 17.5 K. And my VOV was 0.2. So I plug those numbers in, and this is number 11. And I get, what is the voltage gain? It is negative 14, I believe, volts per volt. So we've got the voltage gain. And remember the voltage gain. How was it defined? AV equals V out of T over Vn of T. And Vn of T, what the heck was Vn of T? Is just this VGS. This is Vn of T. So if I want to find V out, I multiply Vn times negative 14, and I get negative was 10 millivolts, 140 millivolts times the sine of 2 pi times 100 kT. Which that negative, having that negative sign in there just kind of bothers me. So we could write this as 0.14 sine 2 pi 100 kT plus or minus 180 degrees. It doesn't matter, it's the same thing. And that would be in volts. So that negative sign can also be represented as a phase shift. What happens, oh, we've talked about this. If we crank up VGS and we keeping the same VGS, let's look at this graphically. There's got to be a good graph in here somewhere. There's been like hundreds of them. Voltage transfer curve. If we crank up yeah, here we go. So let's just erase all this. I'm not going to stand it anyways. If we crank up VGS, we keep the same DC value. No, great, it's not working. Oh, that's because I'm using the eraser. I keep the same DC value here, and I make this signal bigger. Let's say I make my VGS so big that it does this. There's my new VGS, something like this. What happens here is in this part of the signal, I'm in cutoff. So I actually, my output can only go to here. My output's going to look something more like a flattened triangle. No, I can't draw it. It's going to look more like a flattened triangle. If I try to make my input voltage too high, my output voltage is going to throw the transistor out of saturation and cause my amplifier to saturate because I reach the limits of operation on this device. Does that make sense? No, anybody complaining or not? Nobody's complaining. Great, you'll have fun with this on the exam. I think we're almost done. Yes. Eventually, I'm going to throw the amplifier out of saturation and it's going to cease amplifying. It's going to hit those power supply rails. My output can't get above VDD, and it can't get so low. VDS cannot get to be so small that it's less than VGS minus VT. Yes, and you'll get to see all of this on the exam, which is what teachers call assessment. I went to grad school and I got a master's degree in education, then I completely forgot the teacher language because it's just like I get the ideas. I I just don't want to use the teacher language because it sounds dorky. So that is it, because next we're going to look at the small signal model, and that's going to take a completely different thing. So if anybody has any questions about life, the universe, or the homework, let me know. Otherwise, we can call it a day. Oh, who am I looking for? Ibrahim, Lauren, and Jordan Ramirez. Oh, I got a chat. That's probably somebody saying I'm here. Lane Dempsey. Yes, slide 25. And I'll get rid of this. Okay. Okay, I'll see you. More. Okay.
I have another quick question that's not really class related.
Oh, that's great. Go ahead.
I was wondering if you could maybe get some insight. The other day, I have like a door next to my desk, and I have like a light up keyboard that I use for my computer.
All right.
And I went to go, and I've carved it too. I went to go touch the door handle, shocked myself, and the LEDs on my keyboard flashed.
Yes.
Why was that? I wasn't even near I was like standing there.
Okay. So what you did is you generated what's called ESD discharge, electrostatic discharge. If you rub your feet on the carpet, you get and you touch the doorknob, you get a spark. Yeah. That is an actual, can be modeled as a voltage, and if you can feel it, it's like 10 kilovolts. Okay. It's a very high voltage, but it doesn't have any current drive capability. So it's just basically it's a momentary charge. It's a momentary discharge between you and the doorknob. Probably because your screen was close enough, some of the fields off of that, or if you, or as you touch the field, if you touch the screen, it's charged. And the LED works on the LED display.
It was a keyboard, so it's like a light up keyboard.
Okay, so you touched the keyboard?
No, I was standing next to the desk, and I touched the door handle, and the keyboard on the desk lit up, like flashed a light.
Okay, so somehow it got that discharged through the keyboard, and it could have gone through. That shouldn't have happened.
That's why I was wondering, like, how did that?
It probably has. It's probably some. Usually, you have ESD protection on all your devices. It could have been. I can't see why your keyboard wouldn't be ESD protected, but.
It does like randomly. I'll like bump it and it'll just light up like flash. So I don't know. It's not a very.
Yeah. There could be, so mostly devices, electronic devices have ESD protection built into them, but it's usually just diodes. And if some of those are loose or like on one of the keys it got disconnected, something like an ESD event might be enough to light it up.
Interesting. Okay, so that I would ask.
I mean, eventually it could damage the device, but yeah.
Sort of a cheap keyboard, so I'm not too worried about it. Just
okay.
It was like that was interesting. It was in a dark room, and I was kind of like, that's weird.
It could be as simple as there's a bad solder joint, or something like that. Slide 23, yes. There you go. Yeah, it could have been a loose solder joint or something like that. Those solder joints crack all the time. That was 90% of our repairs coming off the line.
I appreciate it. Thank you.
All right. Jordan, yes. You're now marked here.
Hey, I have kind of a similar weird question. So when I worked as an electrician, every now and then I'd be working with live circuits. And I would get 120 volt shocks. And then for some reason, I started building a bunch of static charge, like for like weeks after that. And then eventually I would stop. Like, would there be any reason for that?
Not that I can think of, because yeah, you don't, the 60 hertz, I mean, that should, once you let go of it, the power in the wall, that should dissipate fairly quickly. The way people model your body for ESD discharge is as a very high resistance. There's some capacitive effect in there, but I can't imagine it lasting. I mean, I could think of that maybe lasting for seconds, but not days.
Weird. All right.
Okay.
I have a metal plate in my shoulder too. Could I have done anything?
Uh-huh. Okay. Well, if it's not grounded, but again, it might be capacitively storing up charge somehow. And if it doesn't have a good discharge path to ground, it may take minutes for that to discharge. But I can't see it. And again, I can't see it taking days.
All right. Then it's
Okay.
probably just dry or something.
It could have been. Okay. Let's see. Okay. Stop recording. No, I can just do that by just saying bye to everybody.